So we'll pick right back up talking about two vectors are parallel if the angle between them is 0 or 180 degrees. So let's say I give you these two guys here. We just want to find the angle between them and see what happens. So it's going to be a dot product on top divided by magnitudes. Notice I don't even use the -9 in there because it's just going to give us some wrong answers. If you go to your calculator now, notice how I punch that guy in. So I know square root of something times square root of something. You can just multiply those square roots together. So that's all I did down here. I said square root of 13 times 117. You could break that up into two separate square roots, but make sure you have parentheses in between that to show that it's multiplied or divided by the product of these two. Okay, so it's not 39 divided by this and then everything times this. Comes out to 0 degrees. Okay, those guys got to be parallel. Another way to look at it is say vector W is nothing more than 3 times vector V. Triple -3, you get -9. Triple 2, you get 6. Okay, so you can see connections with those there. All right, if they're not parallel, if they don't have an angle in between them, they could be perpendicular. Now this one's even easier. It's just the dot product equals 0. So think about the formula. And then this is divided by, the product of the two magnitudes down there. If you get the dot product to equal 0, it won't matter what this number down here is. It's just going to go to 0. So if you get cosine of alpha equals 0 and you inverse this, theta is going to be 90 degrees. Well, that's exactly what orthogonal is. These guys intersect or interact with each other at exactly a 90-degree angle. So you do your formula, you find 90 degrees, yes, they are perpendicular. If you can simplify it enough to know just the dot product is 0, then you're good to go there. Okay, so if they interacted to 0 or 180, they're parallel. 90, they're perpendicular. Anything else, the formula will tell us. There's kind of a picture of what these would look like if you were to put them to scale on a grid. They look like they're perpendicular, but you can't always assume so. So make sure you go ahead and you're doing the work, with the formulas or whatnot. Okay, but at least it'll give you an idea. If you drew it to scale, and let's say this guy came up here, okay, there's no way they're going to be perpendicular. You could just say no. Okay, this last thing here is the projection. Okay, and this is a lot of overlap with physics. It's a formula. It says if V and W are two non-zero vectors, the vector projection of V onto W is this formula right here. Projection of V onto W, the dot product divided by the magnitude squared, all multiplied by W. Okay, it's really best explained here on 624. So if we go here, okay, many physical applications, it's necessary to find how much of a vector is applied in a given direction. So look at this figure here. The force due to gravity is pulling straight down towards the center of Earth on a block. So you get a block here on an incline, gravity is going to pull it in this red one straight down. Okay? To study the effect of gravity on the block, it's necessary to determine how much of F is actually pushing the block down the incline. So what's gravity doing to make this thing go down the incline here? Okay. And how much is pressing the block against the incline at a right angle to the incline? Knowing the decomposition of F when often will allow us to determine when friction is overcome and the block will slide down the incline. Okay, So suppose that blah, 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 and it breaks down into this. So basically, what they're saying is if you have a block, okay, so we switch directions here, and it's sliding down a plane or anything. Gravity's this red one pulling it straight down, okay? But it doesn't slide straight down, it slides down at this angle. But there's also this perpendicular component to it here. So what we do to get some of these formulas is we take this picture. All I did to get this one is just drew the other one in a better angle. Okay, so if I take that one up top and I rotate it, you get to here. So this W represents the block that it's going to be sliding down. Okay, this V represents what gravity's doing. The V1 is what's happening coming down this way, and the V2 is that perpendicular thing. You're back to the formula, the projection of V onto W. So how much of this gravity is being projected in this direction? So what we do is we make a perpendicular wherever gravity, whatever this gravity thing would kind of end at, and we drop this guy perpendicularly down, and we move the V2 over there. Okay, it leads us to this. We're going to dot them, divide it by the magnitude squared, and multiply it by W. So we're taking that gravity and we're breaking it down into the two vectors, the one perpendicular to the block and the one sliding down it. Okay, V1 is going to be parallel, so that's going down the incline, and V2 is perpendicular. Okay, so we have the formula here. Here's how you find V1. It's simply just using this formula. You're projecting V onto W. So here's the block. Okay, we've tilted this picture again. The V1 is the projection of this guy down to here in that direction. Okay, now to find this V2, all we did is say if you took V1, you added V2 to it, and you found that resulting vector, it would be V. So if we can say V is just the sum of V1 and V2, in order to find V2, all we got to do is subtract a V1 from it. And it comes from that stuff we did yesterday, going tip to tail with vectors. All right, it's going to be best illustrated here with an example. So find the vector projection of V onto the W and decompose it into two vectors, V1 and V2, where V1 is parallel and V2 is orthogonal. So again, you'll have formulas, you just have to be able to use them. So we want to figure out how much of V1 is being projected onto W. So we're just going to use our formula here. It's going to be the dot product of these two guys. Two times 1 plus 1 times 1 is 3. Now we're going to need the magnitude of W squared. So let's go find the magnitude of W first. So if we now want the magnitude of W squared, it's just going to be 2. We have to take that now and dot it with, or multiply it by W here. So vector W is an I plus a J. And picking up here quickly to finish up in part 3, we'll find the V2.